Good, thank you. Thank you very much for the introduction. My name is Ricardo Vinuesa, as it was mentioned, and I work at KTH, the Royal Institute of Technology in Stockholm. And the research that I'm going to be talking about today on AI, CFD, and sustainability. I'm also going to mention some things about interpretability, which was discussed in the introduction as well. This is funded by the Swedish E-Science Research Center, CERC, and also the Göran Gustafsson Foundation. So I'm going to divide the talk into two different parts. First, I'm going to talk about how to use AI for sustainability, and then I'm going to talk about some examples of practical applications of AI, particularly for non-intrusive sensing. And I will tell you more about that, and then I will be discussing some of these fluid mechanics examples. So first part about AI and sustainability. We basically wanted to answer a question, the question of what is really the impact of artificial intelligence on the 17 Sustainable Development Goals of the United Nations. These goals are, they were developed in 2015 as an agenda for sustainability to be achieved 9 years from now. And each of these goals is subdivided into a number of targets. So we have in total 169 targets that the UN has established as a priority to achieve in the next years, hopefully by 2030. And we needed to be able to answer this question, because these goals span a very wide range of disciplines, from avoiding or ending poverty to climate action, things related to the economy and development. We needed a quite broad multidisciplinary team to be able to span all these disciplines and all these areas of knowledge. And therefore, we had to really have a quite complete team in place. All the results that I'm going to be talking about today can be found in this article, Vinuesa and others, published in Nature Communications last year, 2020. So here you can get all the information and all the details that I would not be mentioning in so much extent today. This is the team that we put together, again, to answer what is the impact of AI on the Sustainable Development Goals. There's a total of 10 people spanning a wide range of areas of knowledge, from applied AI to more theoretical and fundamental AI, social interaction, ethics, economy, legal aspects, biodiversity, energy systems, and also Max Tegmark, who is a very well-known scientist in the context of AI sustainability and the future of AI. So we had this very complete team to be able to address all these questions, and we had an expert elicitation process to be able to basically have a quite objective view on the possibilities of AI, both positive and both negative. The first thing that we did was to take the 17 goals, the 17 SDGs, and divide them into 3 main pillars. This is a quite a standard classification. So we divided all these goals into the ones affecting the society, the economy, and the environment. Doing so, we can have a much more holistic view of the effects of AI on bigger areas which are interconnected in the context of all of these SDGs. And then, as I mentioned, all these SDGs are subdivided into targets. We have a total of 169 targets. And the idea is that, to kind of summarize the results, we found that AI, artificial intelligence, can help in 79% of the targets, whereas it can have negative effects on only 35% of the targets. However, even if the results are positive, mostly positive, one needs to keep in mind that even one target being negatively affected can have extremely bad consequences, can have catastrophic consequences. So this number, as long as it's not 0, is something that should worry us, even if we should also acknowledge all the potential in the positive side to be able to harness all the possibilities and opportunities from AI. When we look at the 3 categories that I mentioned before, the environment seems to be the one with the biggest positive impact. 93% of the targets can be positively affected by AI in the environment, whereas society seems to have a quite negative potential of AI, with 38% of the targets being negatively affected. So this is also something to keep in mind. And other things that are important are to look a bit in more detail. If we look at each of the SDGs, what is the percentage of the targets from that SDG that are positively or negatively affected by AI? And what I show on the left is for each of the SDGs, the percentage of targets with positive effect of AI. And on the right, the percentage of targets for each of the SDGs with negative effect of AI. We're going to focus first on the light color, and the light green and the light orange, which shows that there is at least one reference in the literature suggesting that there is a positive or a negative effect of AI on that particular thing. Okay, so the light color is the more simplistic analysis, but this analysis can be made a little bit more robust and a little bit more advanced, and is to by analyzing and studying what is the type of evidence that is being found. So references that are quite easy to generalize and quite robust with established methods. Those are references that we call of type A, and that has a weighting factor of 1. And then we can go down all the way to references that are very speculative and not so easy to generalize. And those are references of type D with a weighting factor of 0.25. So essentially, if we have a reference of type D suggesting a positive effect of AI on one target, we would only count 0.25 target being positively affected by this type D reference. Going back to the figure before, what we can do now, and I think is quite interesting, is compare the light and the dark color. So the dark color is obtained when I'm taking into account the types of evidence. And of course, the dark color is the dark area is going to be smaller or equal than the light area because of the definition of the weighting factors that I mentioned before. So what we can see by comparing the light and the dark color, we can actually identify how speculative is the research suggesting positive or negative effect. If we look at the environment, which are all of these SDGs, and the society, which are all of these over here, what we see is that the reduction from light color to dark color in the positive effects is very small compared to the reduction from light color to dark color in the case of negative. This means that the negative effects of AI on the environment and the society are perhaps more speculative and not so well known. However, when we look at the economy, at the SDGs related to the economy, what we see is that the reduction from light color to dark color in the case of positive effects is larger, this reduction is larger than the reduction that you see in the case of negative. This suggests the opposite as before. The positive effects of AI on the economy are not so well documented and perhaps are something that one should study more because this is a clear research gap in literature that we identify in our study. So more particular examples, no? I gave you a little bit the holistic view, kind of like all the ideas and all the possibilities that one can find. But if we go into concrete examples, and again, here I will only mention some of the examples, but a very detailed list with all the references and all the examples can be found here in Nature Communications 2020, yes, this article. Some examples. Well, there is a positive effect of AI on SDG 1 on no poverty, for example, through the use of satellite data to track poverty. And this is typically what we observe. Mostly all the positive effects of AI are because a new technology is enabled, and therefore we can do things that we were not able to do before, which bring about this positive effect. There is also a quite important negative effect on SDG 10, and is the possibility of uneven opportunities to access AI. If the future is going to rely on AI, and if the future economy and development is going to rely heavily on AI, and not everybody has the same access to AI, we're going to be increasing the existent inequalities, which of course is counterproductive and has very negative implications in the context of SDG 10. So this is also something quite important to keep in mind, and we should also focus when we develop AI so everybody has adequate access. More examples. We live challenging times now in the context of Corona. there is quite misinformation going around the internet. And of course, a big aspect that is causing that misinformation to spread so quickly are the AI algorithms of social media that reinforce some of the beliefs that we already have when we go to the network, to the social media that we like to use. So of course that creates political polarization, social polarization, and an increase of the inequalities. So that also has important implications there. And I would say that a very interesting, let's say, implication of this is in SDG 16 on strong institutions, because, well, I mean, we are living at a time that is changing very quickly. AI technology needs to be regulated, yes, but AI technology needs to be regulated by people who know about AI technology. So I would say that regulatory insight is more important than regulatory oversight. We need to involve in this process of regulating AI. Now with the AI Act of the European Union, the guidelines of UNESCO, we need to involve people who know about AI, who know what AI can and cannot do. And we need to establish a very important and very much needed global debate where everybody is aware of what AI can do and what impact it's going to have in everybody's lives. Not only from the perspective of politicians, but also researchers, industrial partners, and the general public, students, universities, everybody needs to be involved in this globally. I want to give another example of a data-driven method with important implications on sustainability, and is the contact tracing apps that were developed last year, and there was quite some debate around them. Of course, they have important implications on SDG 3 on health and SDG 10 on inequalities. And we had an article last year, here in, you can see it on the bottom, Vinuesa and others, Results in Engineering 2020, where we established a framework with the socio-technical requirements that these apps need to have. We divided those requirements, there are 19 requirements in total. We divided them into impact on the citizens, technology, and governance. And we actually analyzed a number of apps. Here I'm showing 3 of them, the Austrian, the UK app, and the Singaporean app. And we see how well they score in all of these criteria. We also analyzed the European Data Protection Board guidelines, and we also saw that they were not as strict. The EDPB, the European guidelines, were not as, let's say, as thorough as what we want in our framework. And if you want the list of requirements, you can find them in the article. Everything is very well explained there. Perhaps an important conclusion comes from the data gathering. The data gathering needs to be decentralized in order to be ethically compliant. And to do that, we encourage the TP3T protocol, which was developed also last year in Switzerland, which is an excellent way to implement this decentralized data. Another aspect is the communication. You need to have an adequate communication strategy in order to have an adequate and meaningful penetration of these apps in the society, which unfortunately was not completely the case during the events of last year. Going back to the Nature Communications paper, all these interactions that I've been talking about can be summarized in terms of 3 agents: the technology, the individuals, and the governments, where the thickness of these arrows are connected to the speed of change, as you can see there. So, of course, technology is advancing very quickly. The individuals are lagging a bit behind technology, but picking up on those new applications, on those new opportunities. And of course, the governments lay far behind. They're very delayed compared to the technology and the individuals when it comes to legislation and possibilities of policy development for this changing reality that we are all living. Everything is happening as well with the environment as an underlying layer, where we are having, of course, resources, exchanging resources, and having an impact on it. And of course, the environment is another important agent if we think now of the current climate emergency that we are in. So, after talking about several examples, I would like to also mention one case, which is SDG 11 on sustainable cities. This was actually a quite interesting realization during this work, because my main area of research is simulation, data-driven methods, and fluid mechanics. I work mostly with fluid mechanics. And of course, realizing during this research that it was possible to use AI to improve the air quality on cities, that motivated me to start research, more, let's say, applied research on this particular area. Also keeping in mind that 800,000 people die in Europe every year only because of the air pollution. So this is actually quite a scary number. And then what I did was to initiate research to try to understand how can I combine simulations and machine learning to be able to reduce the air pollution in cities. And soon we will start in the second part of the talk, which will be more technical. So the first part is a little bit more of overview of what AI can and cannot do in terms of sustainability. The second part will be more technical, and we'll be discussing neural network architectures, performance, predictions, and so on. What I want to do is to do what is called non-intrusive sensing. What is that? Well, let's imagine that I have this obstacle, this building, and these structures that you can see around as the flow that I can simulate with high-performance computing with very high accuracy. And I can use a number of sparse measurements, these black dots. So from those sparse measurements, I can reconstruct the three-dimensional flow that is surrounding this building. And together with the flow, I can obtain, of course, the temperature and the pollution levels in that. This is a little bit a summary of different ways to do it. Essentially, we can apply modal decomposition. POD is a very standard way to do it. And then using LSTMs or convolutional neural networks, then I only need to predict the temporal coefficients of these POD modes, and then I don't need to predict the whole signal to be able to understand what are the distributions of the pollution levels. I can actually use very detailed flow simulations, as you can see on the right. These are two buildings with different separations. You can see all the details of this in this reference, Torres and others in Energies this year. And well, the point is that we can combine these simulations with machine learning to be able to do non-intrusive sensing, as I will be discussing a bit more detail in a second. Before going into the technical part, I wanted to also mention interpretability and how important it is. Of course, deep learning is mostly comprising black box models, which means that we don't know what are the parameters, and we only know what is the architecture and what are the weights that are being trained for this network, but we don't know exactly how the inputs are being used to produce the output. And I mean, there are ways to do explainability in the sense that we can see what is the effect of certain inputs on the output, but we cannot get a full interpretation of those results. And there is a recent article by Cranmer and others from Princeton where they propose a method for interpretability, a posteriori interpretability, which is based on inductive biases and genetic programming to be able to obtain symbolic expressions with an interesting performance compared to what we can get in the neural networks. And then we have an article just accepted in Nature Machine Intelligence, as you can see here, where we basically discuss how we can apply these methods of interpretability in the context of the Sustainable Development Goals to be able to harness all the positive potential of AI and exploit it to the benefit of. Okay. So we have the first example in Nature Communications, and then this one on interpretability in Nature Machine Intelligence. And you can find the preprint also. Now, the second part is about predicting spatial distributions. So doing the non-intrusive sensing, what I mentioned before, of going from the sensors to the three-dimensional flow field. And to do that, we will use mostly convolutional neural networks. Okay. So what I'm showing here is the flow very close to the wall, very close to a surface. And traditionally, people have been using linear methods to establish a connection between the input and the output. So the input would be the wall information, those sensors that I showed before, and the output would be the flow above those sensors. Now, linear methods have one problem, of course, and it's the fact that the flow, the turbulence that we are modeling here, that's not linear. It's a non-linear phenomenon. So, of course, if we use linear methods like linear stochastic estimation or extended POD, then I'm not going to be able to reproduce all the physics in that phenomenon, and therefore the predictions are going to be flawed, as we can see here. In this study by Sasaki and others, where I also participated, this is published in the Journal of Fluid Mechanics, we showed that nonlinear methods can outperform linear methods. And what I'm going to explore here is the possibility of using neural networks, which are also nonlinear methods, to make these predictions. So what I consider is a simple flow, is the flow between two walls. Actually, in this case, it's even simpler. We have one wall and a free surface on the top, so kind of like a channel, like a river channel. And we perform very detailed simulations. For the ones who don't know about fluid mechanics so much, I will not get too technical on the fluid mechanics. But just to give you an idea that I'm simulating at a low Reynolds number, so in a not too turbulent condition, the flow in this configuration, which is the flow over a wall, okay? Turbulent flow that is going on top. And then I'm trying to make predictions in this simplified case, which is a model for the city environment that I showed before. I'm actually working on the city case, and we're getting also good results there, but I'm going to show the simple case first of the simplified channel flow. You can find all the results here in this reference, Guastoni and others, who is one of my students, the Journal of Physics conference series. So before starting to talk about the networks, let me just mention briefly two types of networks. I mean, we can have fully connected networks or convolutional networks. In the case of fully connected networks, we have one neuron in one layer that is connected to all the neurons in the next one. And of course, what happens with this is that we have very large numbers of parameters because all the neurons are connected to each other. So we have very, very large weight matrices and bias vectors, and this can be prone to overfitting the data. You can see one example of using some of these fully connected networks, particularly with temporal dependencies in turbulence, in turbulent flows, in this study of Srinivasan, who is one of my students, and my group in physical review fluids. In the present example, when I'm looking at images and when I'm having instantaneous flow fields of the turbulent flow, then I'm going to use convolutional layers. And these convolutional layers, as many of you in this audience know here, but I'm going to just explain it briefly. As many of you know, in the convolutional network, what I'm having is this little window, which is a kernel, which is typically of size 3 by 3 or 5 by 5. And this kernel is sweeping through the input. Okay, it's been moving through the input. Then I apply what is called a convolution operation, which I will not discuss in much detail, but if you have questions, you can discuss it afterwards. And what happens is that the output is a feature map where each of the points obtains information from 9, in this case, a total of 9 points in the input. What does this mean? This means that we are getting 1 point, 1 output based on 9 points for the input. And this is going to be important later on. What this means is that convolutional neural networks are very widely used in computer vision because they are suitable for the identification of features and spatial information in the data, which in the end is images. So what I'm going to do is that I'm going to take the channel and the flow on top of that wall, and the flow is flowing above, and I have the wall, and I'm going to use the wall information to predict the flow on top, to predict what's happening on top. So essentially, I'm going to use this blue plane over here, the wall, to predict this orange plane over here, which is the flow on top of the wall. And I'm going to use the two wall shear stress components at the wall, which are basically the friction of the air on the wall. And I'm going to predict the streamwise velocity fluctuations at a certain distance. One motivation to do this, well, reactive flow control or closed loop control, where I can design a better flow control to reduce the drag of an airplane, for example, when I understand better what's happening in the flow, because then I can fine tune the type of actuation, the type of control, and adapt it to the particular state of the flow. So this is the architecture that we're using in this study. This is a convolutional neural network. We have 2 inputs, which are the 2 wall shear stress fields. We have 1 output, which is the streamwise velocity fluctuation field, and we have a total of 6 hidden layers. The input has 128 square grid points. We're using the ReLU activation function, which is very widely used in computer vision. And these numbers that you see here, these are the number of stack layers, which are the number of feature maps that I am obtaining. So for one particular filter of the input, what I have is a total of 50 parameters, right? Because, sorry, there we go. I have a total of 50 parameters because I have a depth of 2 and a kernel size of 5 times 5. So I have only 50 parameters that I apply a total of 64 times. And that's much lower than the 33,000 parameters that I would have with a fully connected network. So in the first layers, the fully connected networks are much more expensive. They have many more parameters than the fully convolutional networks. That's why the convolutional networks are much they're more interesting. They are preferred when we are doing computation. Then we apply a total of 64 filters, each of them with 50 parameters, and then each filter identifies what is called a feature. So these features can be regions of streaks, for example, so elongated regions in the flow. They can be regions of strong fluctuation, regions of negative velocity, recirculation. All of these aspects can be identified in the feature maps that I am detecting with a convolutional network. Of course, when I go to the next layer, I have a total of 64 feature maps here, which means that my next kernel is going to be smaller. It's going to be 3 by 3 only, but the filter is going to be quite large because I need a depth of 64 to be able to apply the convolution operation in this next layer. So the total number of parameters starts to increase, and I have 128 filters in this next hidden layer that I'm considering. So something important. As I go deeper in the network, as I go closer to the input, what I realize is that the features that I can identify are larger. Because if you remember from the convolution operation that I mentioned before, when I apply one convolution, each point receives information from 925 points in the input. But when I apply another convolution, another convolution, another convolution, each of the points from the deeper layers are receiving information from more and more points of the input. The receptive field corresponding to those layers is getting larger and larger. And that's, it can be stated that the first layers in this network are identifying features that are smaller, and the layers that are closer to the output are identifying features that are larger. And of course, because turbulence, many of you in the audience maybe don't know it, but it's not, I can just mention it so you can follow the next part. Turbulence is a multi-scale phenomenon, which means that there are small scales, there are large scales of different sizes, and they're all interacting together. So having this possibility with deep neural network to identify all this range of scales is actually very promising. So the convolutional neural networks can be used in two ways. One is to obtain a global output, and the global output can be obtained when I have a fully collected layer at the end. For example, this would be an example of I have a picture and I classify it as a car. And then if I continue with fully convolutional networks, so I don't have any connected layer at the end, then my output is local. So what I can actually do is not only have a classification for the whole picture, but a classification for each point in the picture. So I know that this region is the street, this region are the cars, this is the pedestrian cross, and so on. So convolutional networks with fully connected layers at the end give me global outputs. Convolutional networks that are fully convolutional give me local outputs. Okay, this is very important. So some results. What I'm showing here are the streamwise velocity fluctuation, so the turbulence, at y plus 15, which is a region close to the wall, very close to the location that I'm using as an input. So this is my input, and this plane over here is what I'm showing in this case. The second row is the reference, and you can see that the flow has a certain structure. You can see that the flow has an elongated characteristic, which is these are called streaks. These are structures that exist in turbulence, and this is why convolutional networks are quite good at predicting turbulence because they can identify these features and they can be very good at making predictions from them. At the top, I have a linear method, the linear stochastic estimation, and at the bottom, I have a non-linear method, which is the convolutional neural network. What we can see is that the neural network predicts much better, and they can actually, the linear method is attenuated and it's very smooth because the linear method cannot account for the non-linearities, it cannot account for the modulation effects in the flow, which can be accounted by the non-linear model. So we get not only the streaks and their distributions, but also the details of the modulation effects on those streaks that are present in the flow when I am using nonlinear methods. Now, y plus 30, so these are the same results, but a bit farther away. When I move farther away, what I see is that the linear method gets much worse, and the nonlinear method is still predicting quite well. And if I go much farther away from the input, then the linear method is predicting almost nothing. And it's really, there is not any linear correlation, and therefore that's it has many problems for prediction in terms of the linear method. And the neural network predicts, I mean, it has more difficulties to predict because the correlation is lower, but we can see how the structures are still very well identified together with the possibilities of getting the nonlinearity and the modulation. This is also related to the effect of the time step. So when you get larger scales, when you're farther away from the wall, having a larger time step can improve the results, as we can see here. And what I'm showing now, on the left is the mean flow. On the right is the stringwise velocity fluctuation profile. The black lines are the reference. And if we look at the fluctuations, we will see that the green triangle is the linear method. The linear method is exhibiting large errors everywhere. And the orange and blue are the two neural network cases for different time steps. Essentially, close to the wall, we can have less than 3% error with a neural network, where the linear method gives me more than 12% error in that location that is very, very close. Farther away from the wall, the results of the linear method are even worse. So everything that I have shown so far is related to having two inputs and one output. What I'm going to do now is that I'm going to extend these results to a higher Reynolds number. A higher Reynolds number means that the conditions are more turbulent, so more challenging. And I'm going to have three inputs now. So at the wall, I'm going to measure the two wall shear stress components and the pressure. And at the output, I'm going to measure the three velocity fluctuation components: stringwise, wall normal, and span-wise velocity fluctuations. Okay. Important. These results, everything that I'm going to show in this section is published now in the Journal of Fluid Mechanics this year, also by Bastoni, my student, and other collaborators. So you can see all these results in the Journal of Fluid Mechanics, and this is a quite interesting paper for all the information that I'm going to be providing. So in addition to having the method that I showed before, where I have just a fully convolutional network predicting everything from the input to the output, okay, what I'm going to consider now is another approach based on POD. POD is proper orthogonal decomposition. If you're not familiar with it, maybe you're familiar with SVD, singular value decomposition, or PCA, principal component analysis. These are basically the same algorithm with small variations, but basically the same algorithm. And essentially what we do with POD, with this decomposition method, is that we can go from the velocity signal, which depends on space and time. We can decompose that and express it in terms of spatial modes that are fixed and temporal coefficients which are changing. So in a way, the advantage of doing POD is that I can encapsulate all the spatial information into these modes which are frozen, which are not moving. And then the only thing that I need to predict is the temporal dynamics, but I don't need to worry about the spatial information. Okay. So what I'm showing here at Reynolds top 550, so this is much more turbulent Reynolds number. This is a much more turbulent flow. What I'm showing is the first column, a plane that is very close to the input. So this is the wall, this is the input, and the reference or the prediction that I'm trying to make here is the first column. And in the second column, I'm showing an output that is much farther away. Okay, so close to the wall and far away from the wall. Of course, when I'm far away from the wall, the correlation between the input and the output is lower, and therefore the predictions are expected to. The third row, which says DNS, that is the reference, that is the simulation. This is what I'm trying to reconstruct. And then the first row is the linear method, which is called here extended POD, but that's formally equivalent to the linear stochastic estimation. So it's a linear method. And we can see that the comparison of the linear method, which is the first row, with the reference, which is the third row, is quite bad. Right? The linear method is really unable to predict this physics because the flow is much more chaotic and complex than what can be obtained with a linear method. The last row is the FCN. That's when I'm using the whole signal to predict the whole signal without any modal decomposition. We can see that close to the wall, this method, the FCN, is in extremely good agreement with reference. Far away from the wall, there is a bit more deviation. And the second row, which we call FCN-POD. FCN-POD is the case where I'm using the network, but I'm also doing the model decomposition, so I only need to predict the temporal dynamics. I don't need to predict the spatial information. We can see that close to the wall is not as good as the FCN method, but far away from the wall, it's better. So the FCN-POD works very well far away from the wall, and the FCN works very well close to the wall. This is also confirmed when we look at the statistics. Again, in this case, the black lines are the reference. And what I have is the stringwise, wall normal, and span-wise velocity fluctuations. The triangle is the FCN method, the circle, the FCN-POD, and the square is the linear method. Okay? What we can see is that close to the wall, with the FCN method, we can predict the near wall fluctuations with less than 1% error, which is really great. I mean, that's something very good. Far away from the wall, all the results get worse, but it comes to a point where the FCN-POD is predicting slightly better with like 15% error or 25% error, is predicting better than the FCN. Why is that? Because the POD is encapsulating the spatial information in those modes. And when you have large scales far away from the wall, the most efficient way to predict that is to encapsulate it into those spatial modes. When you're very close to the wall and you have a larger variety of scales, then it's not worth it really to do it like that. Then it's not really worth to, in a way, to encapsulate the information in those modes. It's just easier to predict the whole signal. So if your signal is close to the wall and it's more chaotic, the FCN is better. If your signal is farther away and there is more structure in the larger scales, then it's better to use the model decomposition approach. Okay. Now, this part over here is something that I consider some of the most interesting results of this study, and it has to do with transfer learning. So when we do transfer learning, what we want to do is use the information that has been learned in one scenario, so the weights that have been obtained in one scenario, to be able to extend them to another scenario. In this case, what we do is that we train a network at y plus 15, so close to the wall. And what we do is that we want to make predictions farther away from the wall. What we're going to do, because as I mentioned before, the first layers identify small scales and the last layers larger scales, is that I'm going to freeze the first layers. So for the prediction far away from the wall, I'm going to use the same weight in the first layers as those that I used in the predictions close to the wall, and I'm going to only train the 3 last layers. Doing so, and you can see all the details here in the Journal of Physics conference series, what we get is very similar performance, but at 1/4 of the cost. So we can reduce the training time of this network by a factor of 4 through training only the 3 last layers and freezing the 3 first ones. This is even more interesting when I'm considering doing transfer learning, so transferring the weights from a low Reynolds number to a high Reynolds number. So a non-very turbulent condition to a much more turbulent condition. In this case, what I do is that I'm comparing the loss function in the case where I initialize the training randomly, or when I initialize the training from the weights that were obtained at 180. Yeah? So I do the simulation at low Reynolds number, I take those weights, I do the training at high Reynolds number, and the initialization is done from the weight that I obtained. If I compare those two, by doing transfer learning, so by reusing the information that I had at low Reynolds number, I can get the same results with 25% of the training data. What does this mean? Well, it means that, of course, the simulation at high Reynolds numbers is much more expensive, so it's much more difficult to obtain data. But this means that I can simulate a lot at low Reynolds number, which is very cheap and very easy, and then reduce by a factor of 4 the need of training data at high Reynolds number. This is very important because Of course, the training time and the simulation, all of this has an environmental impact and electrical consumption. And if we are able to minimize the impact of the model development that we have, then we are doing a favor to the planet. So this is actually a quite good approach. And this again can be found in the Journal of Fluid Mechanics in this article by Washington. A little bit more. We can actually do, if you remember the example from before of the building, I was considering the building with the ground and then sparse measurements, these black dots. But what I have done so far is consider that I know all the information on the bottom, the whole plane, to make predictions. In practice, that's not the case. In practice, I don't know everything at the wall. I know only few sensors, which are the black dots that I showed before. To be able to do predictions in this case, when I don't have all the information at the wall, we can use something called generative models, in particular, the very well-known GANS. GANs are what is called generative adversarial networks. These are networks that are very popular in the context of super resolution, and you can get a little schematic representation here. What we have with these networks, with GANs, is that we have two different networks. On the one hand, we have the generator, and the generator, in this case, receives as an input a low-resolution image, and it has to produce a high-resolution image, using as a reference the correct high-resolution images. And this is a generative model, which means that it's aiming at reproducing the statistical properties of the reference database. In this case, the reference high-resolution pictures. Then the discriminator, which is the second network, its job is to compare the original high-resolution images and the ones produced by the generator and identify which ones are real and which ones have been created by the generator, which ones are real and which ones are fake. These two networks are trained using game theory in such a way that we oppose each other. So the generator is getting better and better at making fake pictures, and the discriminator is getting better and better at identifying those fake pictures. And what we obtain with this is what I'm showing here. All of this work is actually published also this year in Physics of Fluids, WEMS and others. So that's here you can obtain all this information. And what we see is that we have the three low-resolution inputs. In a first step, I obtain high-resolution inputs at the wall, and those high-resolution inputs at the wall are then used to predict the high-resolution fields far away from the wall. So I start from the input at the wall in low resolution, I obtain it in high resolution, and then I use this input to predict here far away. Some examples of this. Well, I'm going to show you the wall reconstruction. So basically the potential of obtaining high resolution data from the low resolution one. Here is the DNS, here is the reference. I'm showing the instantaneous wall shear stress distribution. In the first row, I'm showing the input, which is downsampled by a factor of 4 squared, 8 squared, or 16 squared. And in the second row, I'm showing you the prediction. So we're comparing the second row with this over here. What is very interesting is that even in this case of 16 squared, where I have few measurements, few sensors, you can see that this is very, very coarse compared with the original signal. We can actually get a very, very good reconstruction. Not only that, we can get a very good idea of where the structures are and their locations and sizes. Even if the turbulence is a bit attenuated, as you can see by comparing this and that, even if it's a bit attenuated, the results are realistic and are physical. So that's in principle enough to obtain good representations and good pictures. So this GANS is certainly a very valuable tool to be able to obtain good results in terms of super resolution of turbulence. And these are some future applications that we're working on. Subgrid scale modeling, inflow conditions, tracking of turbulent structures, nonlinear model decompositions, and also flow control and non-intrusive cells. So certainly turbulence and fluid mechanics can benefit from machine learning. We have many, many articles and many studies that are ongoing on how to identify this potential, and we really see the possibility of benefiting from the potential of machine learning. And this is my conclusions. I would like to summarize a little bit what I told you. We first look at AI and sustainability, and we have 79% of the targets with positive effects, 35% with negative effect. So there is a very much needed global debate. We showed that CNNs are a very good tool for reconstruction of turbulence, for understanding the spatial distributions of turbulence. We can get the near world peak with very high accuracy. And so we can actually get, with less than 1% error, we can get much better results than with linear methods. We have some directions of improvement for the future, which I'm listing also here. I would like to thank you very much for your attention. And this is my information if you want to contact me. So I'm always very happy to keep discussing then after the seminar, to stay in touch. So this is my email. You can see here. This is the web of my group, universalab.com. And this is the information of my social media as well, which I also use quite extensively. So just feel free to contact me if you want to discuss anything else. And yeah, thank you very much for your attention. And if you have any questions, I'm very happy to take them.